problem. 1 10 to the 6 gallon reactor is used in a water reclamation plant. This is like a place where you treat the wastewater for reuse for irrigation. So the volume is 1 10 to the 6 gallon. That's the volume. And it is a reactor, so it's a tank. The influent concentration is 100. So the reactor, the volume is known. The influent concentration is 100. CI is 100 milligram per liter. The effluent coming off, C out, is 25 milligram per liter. And the flow rate through the reactor is 500. The flow rate is 500. The flow rate is 500 gallon per minute. Well, the flow rate here and the flow rate here should be the same. What is the first order rate constant for decay of BOD in the reactor? So he need to find out K. K is unknown, and he need to know the first order rate constant. Okay. So we will do. This is like an actual CMFR because there is continuously flow in and flow out. So if you put the equation VDC over DT equal QCI minus QC out minus VKC out, because first order, as you said here, it's a first order rate, so we need to find out that K. Steady state, so this is 0. So Q is known, 500 gallon per minute. Okay, gallon per minute. And the concentration N is 100 milligram per liter minus QI, Q out, I mean the same thing, 500 gallon per minute times C out. C out is 25 milligram per liter minus volume. We know the volume is 10 to the 6 gallon. And that's good. It's consistent with all the units all over the equation, times K. K is the unknown. Times C out. C out is 25 milligram per liter. You can see milligram per liter, milligram per liter, milligram, okay, fine. Gallon is fine. Now, per minute. So the K, it will be per minute. Okay? So we will find the K. And the K, let me just calculate this K here. Hold on. So let's just put the calculator. And that is, so that's going to be a very small 0.0015 per minute. You could convert this to per hour by multiplying this by 60, and that will give you 0.09 per hour. So this is K for the first part of the question. A. Now, assume, because he wanted here per hour, so okay. So we did that because it looked nicer. You could do it per day because there is 24. You could do it per day. It will be 2.16 per day. But since you want an hour, so we do it per hour. B, assume the reactor should be modeled as a blood flow reactor with a first order decay. not as a CMFR, okay? So now we should put the equation for a plug flow reactor. C out is equal Cn e to the power minus k T. What is C out? C out is 25. What is Cn? 100 milligram per liter. E minus K. And what is T? T is unknown, so we have to find T. Well, do you know how to find T? Remember T from the plug flow reactor. T is equal volume. T is equal volume over Q. So what is volume? Volume is 10 to the 6 gallon, and Q is 500 gallon per minute. This is the time it will take this water to stay inside the reactor. So 10 to the 6 over 500. Okay? And then gallon with gallon, you'll end up with minutes. So time is equal to what? 2 10 to the 3 minute. And that is the time. So we'll put this here, 2 10 to the 3 minutes. Now, which means that K would be what? The number over minute. Okay? So you do 25 over 100, which is 0.25, equal e to the power minus k to 10 to the 3, and then you do ln 0.25 minus k to 10 to the 3, and then you do the ln 0.25 divided by 2 to the 3, and then you'll find k. K would be equal to 6.93 10 to the minus 4 per minute. What did he want it in? What must be the first order decay rate constant within that's it. He did not want it. He did not want it in. Assume that the reactor should be with the first order decay. Not as in that case. What must be the first? He did not ask. So we'll do it per minute or per hour because the same thing we did before. So you multiply it by 60 to make it per hour, so 0.042. Now this is K for the plug flow reactor. Now you can see 0.09, 0.042. Well, 0.09 is extremely active. Let's look at C. It has been determined that the outlet concentration is too high. So this outlet concentration, the EPA said that this is too high. Okay? So the residence time in the reactor must be doubled. Okay? So we should double T, the time. It has been determined that the outlet concentration is too high, so the residence time in the reactor must be doubled. Assuming all other variables remain constant, what must be the volume of the new CMFR? So we have to solve it in a way that remember the time is equal volume over Q. If we double time, if you double the time, and of course, let's say, and make Q constant, what is the output? The output, that volume will be doubled. Volume will be doubled. Okay, so now, what will be the volume? If the volume is 10 to the 6, the volume would be 2 10 to the 6 gallon. Okay, so they just want to double the residence time, and this will make sure. You could go ahead and check it with this volume, and you will see that the C out will be much smaller than 25 milligram per liter. You're gonna have the waste. You're gonna have the waste have enough more time inside the reactor, so this will be reduced to a minimum value. Thank you very much. We'll see you in the next problem.